Okay, welcome into our next lesson. It's all about independent events and their probability. Have you ever been in a situation where you're on a boat and, or maybe you're in class and your class is playing bingo, okay? And you get five in a row, you call bingo, you win, and then someone says, "Oh, you're lucky, you should go buy a lottery ticket." Well, like winning bingo and winning the lottery are two completely independent events, so one does not have an effect on the other. Okay, so that's what we're going to be talking about today. Okay, so remember from last lesson, if we were to uh, roll a pair of dice and want to find the probability that the sum is less than 5 if we know that one of the rolls is already a 2. This is conditional probability, okay? Because we have a condition, right? We already know that one is a 2. Okay, so our second roll is dependent on our first roll, okay? So if we just want to do that quickly, remember we need to do the dice table, which if you look at the formula sheet for Unit 5, I've included it there. Which I think I need to post in the main content section, so sorry about that. But it's at the beginning of all your tests and quizzes, okay? That'll always be there for you. Okay, so if we roll, this will be our first roll. And going across will be the second roll. Okay, so if we roll a 1, then a 1, the sum would be 2. If we roll a 1 and then a 2, it'd be 3, 4, 5, 6, 7, then a 2, and then a 1 would be a 3. 2 and 2 is 4, 5, 6, 7, 8. 4, 5, 6, 7, 8, 9. Oh, sorry, not 4. I should move this 9 over a bit too, just to space them a little bit. 9, 5, 6, 7, 8, 9, 10. Then we'll have 6, 7, 7, 8, 9, 10, 11, 8, 9, 10, 11, 12. Okay. So we'll use blue for our first thing. So this is going to be the probability of A. And we know that one of the rolls is a 2. So our first roll is a 2. Okay. And how many outcomes do we have here? Oh, sorry. We know that one of the rolls is a 2. So it could either be this one, or it could be our second roll that was a 2, right? It doesn't specify that's the first. It says that one of the rolls. So it could be our first roll or our second roll could be 2. We don't know which. We just know that one of them is a 2. Okay, so the probability that we rolled a 2, how many different ways do we have it? We have 1, 2, 3, 4, 5, 6. 1. We've already counted this 2. Remember, we don't want to double count it. So we'll go 1, 2, 3, 4, 5, 6, 7. Skip that. 8, 9, 10, 11. We have 11 out of 36. Okay. Actually, I might, oops, got rid of that 3 by accident. I might circle them just to make it a little bit clearer. 3. Okay. So if I rolled a 2, I could have this 3, the 4, the 5, the 6, the 7, the 8, or I could have this 3. I've already circled this 4, so I don't want to circle it again. 5, 6, 7, 8. So how many numbers have I circled? I've circled 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I've circled 11 numbers. There's 11 outcomes we can have that when we roll a 2. Okay. And now we want to find that the probability is less than 5. So probability, or the sum is less than 5. Okay, so that's going to be our B, and I forgot to label that one was A. Okay. But we're only looking at when it's already a 2. So the probability of A and B would be this 3 because we rolled 2 and it's less than 5. This 4 because we rolled 2 and it's less than 5. And this 3 because we rolled a 2 but it's less than 5. Okay. It doesn't say less than or equal to, so that's why we don't include the 5. So we only have 3 that are circled here. of the 36 total options that are both less than 5, and we roll a 2 with. Okay, so if you don't remember our formula from last lesson, it was probability of B given A is our conditional formula, is probability of A and B all over our probability of A. Okay, which our probability of B and A was 3 out of 36, and our probability of A is 11 out of 36. If we have the same denominator in both spots, we can cancel them out. And we will just be left with, actually, I've been red, 3 out of 11, and that's already in those terms. So probability of B given A is 3 over 11. Okay? Remember, this is conditional probability. Now we're going to start looking at independent probability. So when two events are independent. Okay? So here we have that a die is rolled and then a coin's tossed. We want to find the probability of getting an even number followed by a tails. Okay? And we're going to use a tree diagram to do it for the first one. Okay? So first, let's just make the tree diagram. So let's look at our die. So if you roll a die, we can have 1, 2, 3, ish, probably space a little bit, 4, 5, and 6. Okay. There's my stem. When we roll our die, we have 1, 2, 3, 4, 5, and 6. Then, when we toss a coin, not to our witcher, but just toss a coin, you can either have heads or tails. Okay. So we can roll a 1, then have heads, or we can roll a 1 and then have tails. We can roll a 2, get heads. We can roll a 2, get tails. We can roll a 3, get heads. We can roll a 3, get tails. We can roll 4, get heads. Roll 4, get tails. We can roll 5, get heads. Roll 5, get tails. We can roll 6, get heads. We can roll 6, and get tails. We're squeezing at the bottom. Okay, so here's my tree diagram. Okay, it's a little off here. I'll fix where the coin is written. So this is our outcomes when we roll the die, and then this is the outcome when we toss our coin to the witcher. Okay. So we want to find the probability of getting an even number. So circle that in blue, followed by getting a tails. Okay, so this will be A, and then this will be B. Okay. Actually, let's just call it, just make it a little bit easier to let me know which is which. We're going to call this one E, and this one T. Okay, so let's follow along. Let's circle, when we roll a die, even numbers. We have 2, 4, or 6. Okay, they're all even. And then we have to roll a tails after that. So we need to roll a 2 and then get a tails. Yep, I'm still in the call. Okay, or we roll 4, then get the tails. That's going to be right here. Roll 6, then get the tails. That's right here. Okay, so let's do green here. We're looking at the probability of getting an even number and a tail. So followed by, we need the 2, or we need the even and the tails. Okay, that's going to be equal to, how many ways can we do it? We have 2 even, then tails is 1, 4, then tails 2, 6, then tails is 3. So we have 3 ways of getting it out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 different ways. Okay. So the probability is, in lowest terms, 1 over 4. Okay. So the tree diagram works. It gets us our answer, or we there is an easier way. Let's go back to blue. Or what we can do is get the probability of rolling an even number and then multiply that by the probability of getting tails. Okay. Because we have 1, 2, 3 different ways of getting an even number. Out of the 6 total options. Sorry, just near my dog barking in the background. And then we're going to multiply that because remember it's and. That's why we multiply. Okay. If we flip a coin, there's a 1 in 2 chance that we get tails. And now we just multiply the fractions. So that would be 3 times 1 is 3. 6 times 2 is 12. 3 over 12, which is equal to 1 over 4. Okay. So we get the same answer both ways. And multiplying those two together is a lot easier and a lot faster than making a whole tree diagram. Okay. So if two events, A and B, are independent events, then the probability of A and B, remember that's the intersection, so that is and is equal to the probability of A times the probability of B. Okay. So just note, if A and B are independent events, and the probability of B, if the probability of B does not affect any change in A, then the probability of B given A is just the probability of B, okay? Because A has no effect. A has no effect. B, okay? So even if we know what A is, it doesn't matter because A doesn't affect B. So it's just a probability of B. Like if I know in that last example, if I knew that I rolled a 3, the probability of getting a tails still doesn't affect it because they're two completely independent events. Okay. So example number 2. A pair of dice is rolled. Find the probability of getting a sum of 7 followed by a sum of higher than 10. Okay. So let's just make our table again quickly. 3, 4. If you want to use the one from the previous page, you can do that. I'll just have to remake one here. 3, 4, 5, 6. Okay, 2, 3, 4, 5, 6, 7, 4, 5, 6, 7, 8, 10, 7, 8, 9, 10, 11, 8, 9, 10, 11, and 12. Okay, here we go. Okay, so we're rolling 2 pairs of dice. Okay, so the probability of A, or sorry, we'll say let's gain a sum of 7. That's going to be A. And getting a sum of 10 or higher will be B. Does it matter what our first sum is? Is that going to affect what our second sum is? No, it doesn't at all. They're independent. Our first roll doesn't affect our second roll at all. Okay? So let's see, blue, how many different ways can we get a sum of 7? Well, if we roll a 1 and a 6, that gives 7. If we roll a 2 and a 5, that's 7. 3 and 4 is 7. 4 and 3 is 7. 5 and 2 is 7. And 6 and 1 is 7. Okay. So our probability of A is 7 over 36 total options. Okay. Probability of B. We are looking for a sum of 10 or higher. So we're looking for 10, 2, 3 tens or higher. 11 and 12 are all higher than 10. So we have, oops. Sorry, I hope you're yelling at me because I was looking at the sevens, but there's 6 different ways. There's 6 different ways of rolling a 7. Okay. And then we have 1, 2, 3, 4, 5, another 6 options here. Okay. So we have 6 out of 36 ways to roll a 10 or higher. Okay. So the probability of getting A followed by or and then B after it is going to be the probability, because they're independent, probability of A times the probability of B. So what we're going to do is we're going to multiply these two together. We're going to multiply 6 over 36 times 6 over 36. Okay. And what actually might be easier for this one, since we're multiplying, I'm just going to reduce them down to the lowest terms. It's 1 over 6 times 1 over 6, which is 1 over 36. Okay. So the probability that I get a sum of 7 followed by a sum of 10 or greater is 1 in 36 chance. Okay. And now our last example. A card is selected from a full deck of cards, is then replaced, and another card is selected. Okay. So find the probability of getting a king, then a heart. Now, because it is replaced, that means that they are independent events. Okay. Because we're assuming it's just randomly selected and then randomly put back and then random selection again. Okay. So the first card we take doesn't depend on the second card that we take. Unlike when we're taking one without replacement, they were dependent on one another because it mattered what our first card was. Okay. So we want to find the probability of getting a king, followed by the probability of getting a heart. Okay. So remember, there's 52 cards and a deck of cards, so they're both going to be over 52. There's one king in each suit. There's 4 suits, so we have 4 kings. So 4 out of the 52 cards are kings. There's 13 cards in each suit, ace to 10, then jack, queen, king. So 13 of those 52 are hearts. Okay? Because they're independent events, the probability of getting a king and then getting a probability of getting a heart is the probability of a king times the probability of getting a heart, which would be 4 over 52 times 13 over 52. Don't know what that's right in there. And you can multiply these together in a calculator. I don't have one on hand, so I'm just going to kind of reduce the lowest fractions. That'll be 1 over 13 times, that would be 1 over 4. 1 times 1, which is just 1. And 13 times 4 is 52. Okay. So if you're trying to get a king and then get a heart after that, you have a 1 in 52 chance of doing that, as long as the card is replaced. Okay. Now let's look at the probability of getting an ace, followed by the probability of getting a face card. Okay. So let's see the probability of getting an ace. Let's call it probability of A. Oh, sorry, I forgot to label these last time. So we're going to call that one king and that one H. And call a face card F. Probability of F. Okay. So remember, 52 cards, so they're both of the denominators are going to be 52. How many aces are there in a deck of cards? 4 aces. Then the probability of getting a face card. Well, there's jack, queen, king in every suit. So there's 3 face cards in each of the 4 suits. And 3 times 4 is 12. So there's 12 face cards total in the deck of 52. So if you're locked in that, the probability of getting an ace and then a face card, that would be the probability of getting an ace followed by the probability of getting a face card. Okay. So we'd have 4 over 52 times 12 over 52. Okay. If we bring these down to lowest terms, that would give us, that was 1 out of 13 times, this was 3 over 26. They are both divisible. No, not 26, sorry. Just 2 divided by 4 again. Oops. Over 13, which would give us 3 over 169. So there's a 3 in 169 chance of getting an ace followed by a face card. Okay. For those of you wondering if this is how you can count cards, not really. That would be more conditional probability because you know some cards have been taken. So based on what cards are on the table at the time, you can try to calculate what's remaining in the deck. Now, no, I don't endorse gambling or counting cards at all, but that is what they do. So they wouldn't use independent events because they're not independent because the cards aren't being replaced into the deck. That'd be more conditional probability. Okay, but again, I don't endorse gambling. You're not of age, and I don't endorse counting cards either. Okay, with that, that's the end of this lesson. I hope you enjoyed it and have a great day.